Hello, this is Serene from Exam Help Lab. Today I'll be solving Physics Paper 2 AS Level Structured Questions 9702 Paper 2 Variant 1 October-November 2018. Question number 1, Part A, define displacement. Displacement is distance in a specified direction. Part 2, acceleration. So this is change in velocity over time taken. Part B, a remote-controlled toy car moves up a ramp and travels across a gap to land on another ramp. As illustrated in figure 1.1, the car leaves ramp P with a velocity of 5.5 meters per second at an angle theta to the horizontal. The horizontal component of the car's velocity as it leaves the ramp is 4.6 meters per second. So horizontal component of the car's velocity is 4.6 meters per second. The car lands at the top of ramp Q. The tops of both ramps are at the same height and are distance d apart. The resistance is negligible. Part 1, show that the car leaves ramp P with a vertical component of velocity of 3 meters per second. The velocity, which is at theta degree to horizontal, is 5.5 meters per second. This is at theta degrees to the horizontal. The horizontal component is 4.6 meters per second. And the vertical component, which is this one, can be calculated by using the Pythagoras theorem. 5.5 the whole square minus 4.6 the whole square. That leaves us with 3 meters per second. So that's the vertical component of velocity when the car leaves ramp P. Part 2, determine the time taken for the car to travel between the ramps. Okay, so for this part, we should consider the vertical components of the car's jump. When this car leaves ramp P, it has an initial speed of 3 meters per second. That's the vertical component. And acceleration is going to be negative 9.81 since it is rising until this point, until the point when it reaches to its maximum height. And when it reaches to its maximum height, its final velocity will be 0. So time taken would be 0 minus 3 divided by negative 9.81, which is equals to 0.306 seconds. This means that it will take car another 0.306 seconds to reach ramp Q, because this time interval is for the car to leave ramp P and reach its maximum height. And now from this until ramp Q will be another 0.306 seconds. So 0.306 into 2, that will give us time taken for the car to travel between the ramps, which is equals to 0.612 seconds. Part 3, calculate the horizontal distance d between the tops of the ramps. So horizontal distance is going to be equal to horizontal component of velocity into time taken for the car to reach ramp Q from ramp P. So the horizontal component of the velocity is 4.6 meters per second multiplied by the time taken from the previous part. The time taken for the vertical component as well as the horizontal component is going to be equal, so 0.612. That leaves us with horizontal distance being covered by the car is 2.81 meters. Calculate the ratio kinetic energy of the car at its maximum height and kinetic energy of the car as it leaves ramp P. So at car's maximum height, its vertical component of velocity becomes 0, but horizontal component remains constant, and that's 4.6 meters per second. So kinetic energy at this point at maximum height will be half into mass into the horizontal component of the velocity, which is 4.6 the whole square, divided by the kinetic energy of the car as it leaves ramp P. So when it leaves ramp P, it has a velocity of 5.5 meters per second. So half into mass into 5.5 the whole square. And the ratio we get is of 0.7. Part C, ramp Q is removed. The car again leaves ramp P as in part 1, as in part B, and now lands directly on the ground. The car leaves ramp P at time t is equals to 0 and lands on the ground at time t is equals to capital T. On figure 1.1, sketch the variation with time t of the vertical component of the car's velocity from time t is equals to 0 to t is equals to capital T. Numerical values of vertical component of the velocity and t are not required. Okay, so let's first discuss the part where the car leaves ramp P and rises up in air until its final velocity reaches 0 meters per second. It starts with 3 meters per second. So let's suppose I take 3 meters per second over here. And the time interval for this change in velocity was 0.306 seconds, meaning the time interval for the car to leave ramp P and reach its maximum height was 0.306 seconds. And since it's moving against gravity, its acceleration is going to be negative and the acceleration will be constant due to insignificant air resistance. So we'll have a straight line from maximum velocity at t is equals to 0, which is 3 meters per second, until v gets 0 at time t is equals to 0.306 seconds. But we are not required to mention the numerical value, so I'll suppose that 0.306 lies somewhere here, not exactly in the middle because the car is going to travel greater distance later, not from ramp P to maximum height. So we'll have a straight line with negative gradient. Now, as for the part when the car travels from its maximum height to the ground, its initial velocity is going to be 0. The final velocity is going to be greater than 3 meters per second when it was leaving ramp P, because here it's going to travel a greater distance from maximum height until ground level. However, the acceleration remains same, but it is going to be positive this time. So our graph should cross x-axis as the car has changed its direction, and time interval for this change in velocity will of course be greater. So let's say that after a greater period of time, car reaches a speed which is greater than 3 meters per second, maybe somewhere here. This speed is going to be greater than the 3 meters per second. So this time interval is going to be greater. So capital T is the time when it reaches ground level. So we'll mark here. The gradient of both parts of the graph is going to be the same because it's 9.81. So we're going to have a straight line from 3 meters per second until negative something which is greater than 3 meters per second. And the time interval for this negative part is going to be greater than the time interval for the positive part, because from ramp P until maximum height, it covers less distance as compared to that which is being covered after it travels from the maximum height until ground level. Question number 2. A wooden block moves along a horizontal frictionless surface as shown in figure 2.1. The block has mass 85 grams and moves to the left with a velocity of 2 meters per second. A steel ball of mass 4 grams is fired to the right. The steel ball, moving horizontally with a speed of 45 meters per second, collides with the block and remains embedded in it. After the collision, the block and steel ball both have speed v. Calculate v. So before collision, sum of momentum is going to be the momentum of the steel ball, which is mass into velocity, and the momentum of the block, which is going to be again mass into velocity. But since the block is moving towards the left and momentum is a vector quantity, so I'll add a negative sign to the velocity, -2. This is going to be equal to momentum after collision, which is the steel ball has embedded itself into the block. So I'll have the sum of their masses multiplied by the common velocity, which is v, and that's how we get v as 0.112 meters per second. B part 1, for the block and ball, state the relative speed of approach before collision. So relative speed of approach before collision is going to be the sum of these two speeds. We're not going to consider negative or positive signs this time because this is in terms of speed, and speed is a scalar quantity. So 45 plus 2, this is equal to 47 meters per second. The relative speed of separation after collision, it's going to be 0 since they're not separating after collision, so 0. Part 2, use your answers in part 1 to state and explain whether the collision is elastic or inelastic. So for a collision to be elastic, their relative speed of approach before collision should be equal to relative speed of separation after collision. But since over here the relative speed of approach is greater than or is not equal to relative speed of separation, I can say that this collision is of an inelastic type. So you can write that the collision is inelastic because relative speed of approach is not equal to relative speed of separation. Part C, use Newton's third law to explain the relationship between the rate of change of momentum of the ball and the rate of change of momentum of the block during the collision. So Newton's third law describes how two forces will exert equal magnitude of forces on each other but in opposite direction. I can write that after collision, force on ball is equal to force on the block, but in opposite direction. And in terms of change in momentum, force is equal to rate of change of momentum so this rate of change in momentum is equal and opposite for the block and ball. Question number 3, part A1, define power. Power is work done divided by time taken. Part 2, state what is meant by gravitational potential energy. So this is the energy of a mass due to its position in a gravitational field. Part B, an aircraft of mass 1200 kilograms climbs upward with a constant velocity of 45 meters per second, as shown in figure 3.1. The aircraft's engine produces a thrust force of 2 into 10 to the power of 3 newtons to move the aircraft through the air. The rate of increase in height of the aircraft is 3.3 meters per second. Part 1, calculate the power produced by the thrust force. So power is going to be equal to the thrust force into the velocity with which this aircraft is moving. So the thrust force is 2 into 10 to the power of 3 multiplied by the velocity with which it's moving, that's 45 meters per second. And so 9 into 10 to the power of 4 watts of the power is produced by the thrust force. Part 2, determine for a time interval of 3 minutes the work done by the thrust force to move the aircraft. Work done by the thrust force is going to be equal to thrust force multiplied by the distance it moves in the time interval of 3 minutes. So the thrust force is of magnitude 2 into 10 to the power of 3, and the distance it travels in 3 minutes can be calculated by using the formula speed multiplied by time, where the speed it has over here is 45 meters per second and the time interval is in minutes. So we'll convert 3 minutes to 60 to seconds. And the work done by the thrust force is equal to 1.62 into 10 to the power of 7 joules. The increase in gravitational potential energy of the aircraft, this is going to be equal to the mass of the aircraft, which is 1200 kilograms multiplied by 9.81, and the height it rises in the interval of 3 minutes. Over here it is said that the increase in height is 3.3 meters every second. So there's going to be increase in height in 3 minutes. So this will be equal to 7 into 10 to the power of 6 joules. 3.3 into 10 to the into 3 into 60, this is the height it covers in the time interval of 3 minutes, since it covers 3.3 meters of height every second. The work done against air resistance. Now, when you look at the work done by the aircraft's engine and the gaining potential energy, they aren't equal. Therefore, some energy is lost as the thermal energy, and that's a difference between them. So 1.62 into 10 to the power of 7 minus 7 into 10 to the power of 6. The difference between them will be work done against air resistance. So 9 into 10 to the power of 6 joules. Use your answer in B part 2, part 3 to calculate the force due to air resistance acting on the aircraft. So work done against air resistance is equals to force due to air resistance into the distance it moves in the interval of 3 minutes. So the work done against air resistance divided by the distance it moves in the time interval of 3 minutes, because it has a speed of 45 meters per second and time interval is in 3 minutes, into 60. So we get 1.1 into 10 to the power of 3 newtons of force due to air resistance. Part 4, with reference to the motion of the aircraft, state and explain whether the aircraft is in equilibrium. So right in the beginning, they tell you that this aircraft moves with a constant velocity of 45 meters per second. Constant velocity means that there is no resultant force acting on it, and thus this aircraft is in equilibrium. So I can write that constant velocity means no resultant force, and so the aircraft is in equilibrium. Question number 4, part A, state the principle of superposition. So that's when two waves meet, the resultant displacement is the sum of the individual displacements. Part B, an arrangement for demonstrating the interference of light is shown in figure 4.1. The wavelength of the light is 610 nanometers. The distance between the double slit and the screen is 2.7 meters. An interference pattern of bright fringes and dark fringes is observed on the screen. The centers of the bright fringes are labeled B and the centers of the dark fringes are labeled D. Point P is the center of a particular dark fringe. And point Q is the center of a particular bright fringe. The distance across 5 bright fringes is 22 millimeters. Part 1, the light waves leaving the two slits are coherent. State what is meant by coherent. So waves with constant phase difference are called coherent waves. Part 2, state the phase difference between the waves meeting at Q. So point Q is, as told, that is the center of a particular bright fringe. A bright fringe means that there was constructive interference, and hence our phase difference is going to be either 0 degrees or 360 degrees. So I mentioned 360 degrees. Calculate the path difference in nanometers of the waves meeting at P. So P, as told, is the center of a particular dark fringe. So this is a dark fringe. Now, the first thing to be noticed is that this B is the central bright fringe, which will be having a 0 path difference between the incoming waves from these two slits. Now, there's next D, this D and this D. Now, these two Ds will have a path difference of half lambda, which makes them dark fringes. Now, next Bs, which is this one and this one. Now, they will be having a path difference of complete wavelength, 1 lambda, which makes this fringe bright. And now at P, this P and this D, which are dark fringes, they are supposed to have a path difference of 3/2 lambda. And that's why they form dark fringes. Dark fringes appear when path difference is in fractions. So the path difference at P is going to be of 3/2 lambda, where lambda is the wavelength. In nanometers, it's 610. So 3/2 into 610, and the path difference at P is going to be of 920 nanometers. Remember that at the central bright fringe, the path difference from the incoming waves from these two slits is going to be 0. The next dark fringe on either sides will have a path difference of lambda/2, that's half of wavelength. And then the next bright fringe will be having a path difference of complete 1 wavelength, and the next to it would be 3/2 lambda, and then next to that will be again a bright fringe with a path difference of 2 lambda, and that continues. So every time a fraction of path difference occurs means that point will be a dark one, and all the whole number path differences will be all the bright fringes. Part 3, determine the distance A between the two slits. So AX/D is equals to lambda, where A is what we have to calculate multiplied by the distance between the two successive bright fringes or dark fringes. Over here, 22 millimeters is the length between 5 bright fringes. So between two bright fringes, it's going to be 22/4, which is equal to 5.5 into 10 to the power of -3 in meters, divided by the distance between the slit and the reflective screen. So that's 2.7 meters. And our wavelength is 610 into 10 to the power of -9. And so A is equals to 3 into 10 to the power of -4 meters. Part 4, a higher frequency of visible light is now used. State and explain the change to the separation of the fringes. So according to formula, C is equals to F into wavelength. A higher frequency means a shorter wavelength. According to the formula AX/D, when wavelength decreases, X will also decrease, means the separation between the fringes will also decrease. So we can write that wavelength decreases, thus separation of the fringes decreases too. Part 5, the intensity of the light incident on the double slit is now increased without altering its frequency. Compare the appearance of the fringes after this change with their appearance before this change. So there's going to be no change to fringe separations, as it is not directly proportional to, or as it has nothing to do with intensity. It has all got to do with frequency or wavelength. So no change to fringe separation. Though the brighter fringes will get even brighter, and the dark fringes will remain as they were due to increase in intensity. So brighter fringes get even brighter, and dark fringes are unchanged. Question number 5, part A, state what is meant by an electric field. So it's a region around a charged object where another charge experiences a force. Part B, a particle of mass m and charge q is in a uniform electric field of strength E. The particle has acceleration a due to the field. Show that A is equal to EQ by m. So electric field strength is equal to force divided by charge, where force is mass into acceleration divided by charge. And so E is equal to ma by q, and A is equal to QE by m. Part C, a stationary nucleus X decays by emitting an alpha particle to form a nucleus of plutonium as shown. Determine the number of protons and the number of neutrons in nucleus X. So alpha particle has a nucleon number of 4 and a proton number of 2. So X will have a nucleon number of 244 because we have to conserve the charges and the nucleon number on both sides. So 244 and 94 plus 2 is 96. So X has 96 number of protons, and number of neutrons will be the difference between the nucleon number and the number of protons. So 244 minus 96 would leave me with 148 number of neutrons. Part 2, the total mass of the plutonium nucleus and the alpha particle is less than that of nucleus X. Explain this difference in mass. So there's going to be always a difference in masses, but we can write on whole mass to energy is conserved. And some energy is released as gamma radiation. Part 3, the plutonium nucleus and the alpha particles are both accelerated by the same uniform electric field. Use the expression in part B to determine the ratio. So acceleration of the alpha particle, according to the formula in part B, acceleration is equals to charge by mass, since we have kept both alpha particles and the plutonium nucleus in the same electric field. So we are going to ignore E. We'll consider Q by m. Acceleration is equals to Q by m, where acceleration of the alpha particle is equals to charge of alpha particle. Alpha particle has got 2 protons, so 2 into 1.6 into 10 to the power of negative 19, and the mass of it has got 2 neutrons and 2 protons, so 4 into 1.66 into 10 to the power of negative 27. This is the acceleration for alpha particle. Now acceleration for the plutonium nucleus. Plutonium has a notation of 240 and 94. So 94 into 1.6 into 10 to the power of negative 19 divided by 240 into 1.66 into 10 to the power of negative 27. This is the acceleration for plutonium nucleus. Now we'll divide A alpha by A plutonium. So we get a ratio of 1.28. Question number 6, part A, state Kirchhoff's second law. So that's sum of EMF is equal to sum of PDs around a loop. Part B, an electric heater containing 2 heating wires X and Y is connected to a power supply of electromotive force 9 volts and negligible internal resistance. Wire X has a resistance of 2.4 ohms and wire Y has a resistance of 1.2 ohms. A voltmeter is connected in parallel with the wires. A variable resistor is used to adjust the power dissipated in wires X and Y. The variable resistor is adjusted so that the voltmeter reads 6 volts, means 6 volts is the voltage or the PT across this parallel connection of wire X and wire Y. Part 1, calculate the resistance of the variable resistor. The resistance is equals to voltage across variable resistor divided by current across it. Voltage across variable resistors will be the difference in the EMF and the voltage across this parallel connection of X and Y. That's 9 minus 6. And thus the voltage across variable resistor is 3 divided by the current across it will be equal to that across X and Y. So current across X and Y can be calculated by V by R, where V is the voltage across wire X and Y, which is 6 volts, and the combined resistance of wire X and wire Y, which is equals to 0.8 ohms. That gives me 7.5 amperes of current. This much amount of current flows across wire X and Y. This also means that 7.5 amperes of current flows across variable resistor 2. So 3 divided by 7.5, this is 0.4 ohms of resistance. But we calculate the power dissipated in wire X. So power dissipation is equals to V squared by R. Voltage across wire X is going to be equal to voltage across wire Y. So this on whole has a voltage of 6 volts, means 6 volts passes through wire X and 6 volts passes through wire Y. So 6 squared divided by resistance of wire X, which is 2.4 ohms. This gives me power as 15 watts. Part 3, the cross-sectional area of wire X is 3 times the cross-sectional area of wire Y. Assume that the resistivity and the number of density of free electrons for the metal of both wires are the same. Determine the ratio. Okay, so resistance is equals to resistivity into length by cross-sectional area. Area is directly proportional to length, and area into resistance divided by resistivity is equals to length. So length of wire X is equals to the cross-sectional area of wire X. I'll suppose that the cross-sectional area of wire Y is X, so that of wire X would be 3x multiplied by the resistance of wire X, which is 2.4 ohms, divided by the resistivity. This gives me 7.2x by resistivity. Now length of wire Y, I had considered that the cross-sectional area of wire Y is X, so X multiplied by the resistance of wire Y, which is equals to 1.2, divided by the share the same resistivity. This is equals to 1.2x by resistivity. Now 7.2x by P by resistivity divided by 1.2x by resistivity. This gives me a ratio of 6. Average drift speed of free electrons in wire X by average drift speed of free electrons in wire Y. So current is equals to NAVE, and resistance is equals to resistivity into length by cross-sectional area, where average drift speed is equals to current by NAE, where current is also equals to voltage divided by resistance. So we get average drift speed is equals to voltage divided by resistance into number density into cross-sectional area into charge of an electron. Now, for average drift speed of X, this is going to be equal to voltage across wire X, which is 6 volts. So 6 divided by resistance of wire X, which was 2.4, into the same number density into the cross-sectional area of wire X. Is now cross-sectional area of wire X is 3 times the cross-sectional area of wire Y, which I'd consider 3x into the charge of an electron, that is 5 by 36. Now average drift speed of wire Y is equals to voltage across wire Y was 6 again, divided by the resistance of wire Y, which is equals to 1.2 into number density into the cross-sectional area. I had considered that X into E. This is equals to 5 by 6. Now 5 by 36 divided by 5 by 6, that gives me a ratio of 1 by 6. So that was the end of the paper. Thank you for watching.